The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. When you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. Alrighty, so today we're going to go on to section 11.4. After we answer any questions on 11.3, I just want to remind you of a couple of things. So there is class tomorrow, Tuesday. There are no classes on Wednesday, Thursday, or Friday of this week. I don't know that the Math Center is open on Wednesday, not really sure, but anyway, I know there's no classes Wednesday, Thursday, or Friday. So after tomorrow, and I'll remind you of this, but after tomorrow, we won't meet again until the following Monday. So there you have that. Any questions from section 11.3 from over the weekend?
No, you answered my only one on your office hours on Friday.
Okay, how about you, Greg?
No, I don't have any questions. Just plugging numbers in.
Okay, all right. Well, then we'll go on to section 11.4. And I want to introduce that by giving you the following situation. 2 cubed equals 8. 2 to the 4th power equals 16. 2 to what power equals, shall we say, 11? What can you tell me about x? Anything?
It won't be negative.
Okay. Anything else you can tell me?
Is it not a full number?
True. Elaborate on that. You can get a little more specific. It's not like a whole number.
It's like a fraction.
Well, how about this? What two numbers would it have to be between? If 2 to the 3rd power is 8 and 2 to the 4th power is 16, wouldn't x have to be greater than 3 and less than 4?
Yes.
You seeing it? Okay. So we at least know that x is between 3 and 4. Now we could sit down on our calculator and we could go 2 to the 3.1 power, 2 to the 3.2 power, and do that through trial and error and a lot of time and get, as accurate as we needed to do. Or we could take this exponential equation and rewrite it as what is known as a logarithmic equation. And the way that would look would be this: log base 2 of 11 equals x. Now, if you've never been exposed to logarithms before, you're going, what just happened? Well, we're going to talk about that. But what I do want to point out right now is by taking this exponential equation and rewriting it as its equivalent logarithmic equation, I have isolated x. Now the problem is, though, I don't know what log base 2 of 11 is, but we're going to learn over the next few days how we can put that into our calculator to solve the equation, okay? So we'll come back to this particular problem later on. But right now, I want to talk about just this whole idea of how I got from here to there, okay? In fact, this is going to be a two-way statement, meaning that if we have this, we can write it this way. If we have this, we can write it this way. And the way I like to describe this is to use an inning of baseball, okay? I don't know if you're a fan of baseball, but my guess is that you know a little bit about it at least. We'll find out. So let's just talk about one inning of a baseball game. There are two teams. There is a player that is up to bat, and there is a set of players that are up to bat, one team, and the other team is out in the field, okay? After the team that's up to bat gets 3 outs, the players change places. The team that was up to bat goes out in the field. The team out in the field goes up to the bat. Now, in the infield, there are bases. There's home plate, first, second, and third base. Okay. When the team that's out in the field is going to go up to bat, do they go to the infield, pull up the bases, and take them into the dugout? No, they don't. There's an expression called stealing a base, but that doesn't mean you actually take the base out of the ground. The bases stay the same, even though the players change places. Do you follow what I just said?
Yeah.
Yeah.
Okay. Now, let me go back to this problem and let me look at the first equation. 2 to the x power equals 11. 2 is the base. X is the exponent, okay? Now, this logarithmic equation on the right side, this is how I read it, and I'll read it again. Log base 2 of 11 is x. So here, the base is the same as it is here. So the bases are the same, but the players, the x and the 11, changed places. Now, careful. This is 2 to the x power. This is not 2 to the 11th power, even though the 11 is connected with it. This is log base 2 of 11. But the bases stayed the same. The players changed places. That's how I remember how this process works. Let's look at some more examples. Let's say I had 2 cubed equals 8. So writing that equation in logarithmic form, it would be log base 2 of 8 equals 3. How about x to the y equals w? Log base x of w equals y. Do you see how the base is the same and the other two numbers are changing places in terms of being related to the base? Are you okay with that?
Yes.
All right, let's look at some more examples. Let's say I've got log base 7 of 12 equals x. Changing that to an exponential equation, 7 to the x power equals 12. So we can go back and forth between logarithmic and exponential equations. All righty. So now let's take a look at some problems from the book concerning this idea. And here we have log base 7 of 7 equals 1. It says write each logarithmic equation as an exponential equation. Do not solve. This one, there's nothing to solve anyway. But so what's the base?
7.
So this would be 7 to the
7th power?
no.
7 to the 1 or first power equals 7, right?
Yeah. So remember, these change. These two numbers change places. So here the 7 is connected with the 7. Here the 1 is connected. Do you see that, Greg?
Okay, yeah, I see it.
Okay, well, good. You're going to have several more examples to see it anyway, but all right. How about this? Log base 10 of 100 equals 2. So how would that look as an exponential equation? What's the base?
10
So 10. What?
to the power of 2 equals 100.
Correct. All righty. Questions on that one? Let's take a look at another example. Log base 6 of 1/36 equals -2. What's the base?
6
So 6 to the
negative, is it -2 or -2?
either way. We're not in English class, so either way. And what does that equal?
136.
Yeah. And isn't 6 to the -2 power equal to 1/6 squared, which is 136? So it is a true statement. Okay. How about log base 8 of the cube root of 8 equals 1/3? What's the base?
8.
8. 8 is raised to what power?
To the 1/8 or 1/3, sorry.
Right? And that equals the cube root of 8. Is that true? Well, don't you, if you take this and write it in exponential form, don't you get that? Cube root 1/3 power? Yeah.
Yes.
In chapter 9. Okay. Now, this says log 0.01 equals -2. There's something missing. What's missing from this problem?
A power. A base, sorry. A
Base, right. Now, log base 10 is commonly used. It's one of the most commonly used base involving logarithms. So common that mathematicians who are often efficient, use some shortcut notation. So they decided that if it's log base 10, they were just going to write log, and they refer to it as common log. If you have a calculator present, look at your left column, and if you don't, well, you can look at it later. There is a button that says log, and the second function of that button is 10 to the x. So there's a reminder right there that log is equal to log base 10. Okay, so just log is a shortcut of writing log base 10. All right, so now going back to this problem, there's an implied 10, so that means 10 to the -2 power equals that. Well, 10 to the -2 is 1 over 10 squared, is 1 over 100, and isn't this 1/100th written as a decimal? So again, that's true. Okay, how about this? N equals log base b of capital R sub 1. So what's the base?
B.
What's the exponent?
N.
And what does that equal?
R1.
R sub 1, yeah. Okay. So people ask, well, what is a log? Well, it's an exponent. It's an isolated exponent is what it is. All right, let's go the other direction. Let's take this problem, 10 cubed equals 1,000, and let's write that as a logarithmic equation. So log base what? What's the base?
10.
10 of what?
1,000.
1,000 equals
Equals 3.
Yeah. Now, do you have a calculator handy?
Yeah.
Okay, so on your calculator, find the button that says log. Okay, push that button, and you should get this showing up.
Yeah.
Then put in 1,000, close it up, push equals, and you should get 3. Do you?
Yeah, I got 3.
Great.
Yeah.
Okay, good. All right. Let's see here. 3 to the -4 power equals 1 over 81. So that would be log base
-4. 3, sorry, 3.
3 of
1 to the 81.
1 over 81.
Yeah, sorry, that's
Yeah,
right.
it's okay. It's Monday. I've
Sure.
had Mondays all week long. Okay, equals what?
-4.
-4. Good. How about this? M to the n power equals p. So this would be log base
N.
of
P.
equals
N.
n. Good job. Okay, so there's just practice and going back and forth between logarithmic and exponential equations. All right. let's take a look at some problems where we're going to actually solve for the unknown. Let's see here. Log base 7 of x equals 0. It's not 100% foolproof, but it's a darn near that if you have a logarithmic equation that you're solving, you tend to solve it by changing it into an exponential equation. And if you have an exponential equation that you're solving, you tend to change it into a logarithmic equation. So here we have log base 7 of x equals 0. If we wrote that as an exponential equation, what's the base?
7.
What's the exponent?
0.
So what is 7 to the 0 power?
One.
Good job. There you go. Okay. How about this one? Log base 4 of 16 equals x. So this would be 4 to the x equals 16, right? Well, this one's not as easy to see as the previous one, but consider this, okay? Logarithmic functions are one-to-one functions, okay? So they have inverse functions. And because of all this, if we have something in this form, let's say y to the x equals w to the q. Wait, that's not what I want. Let's say y to the x equals y to the q. So they have the same base. We can then assume that the exponents are equal, okay? So what that means is, for this up here, let me rewrite that. If I could write it so that they had the same base, I could then set the exponents equal, okay? My writing got really sloppy there. My apologies. Let's go back here. If I could rewrite the equation so that both sides had the same base, I could then set the exponents equal. Okay, so that goes all the way back here to say that log base 4 of 16 is 2 because 4 squared is 16. All right with that?
Yes.
Okay.
Yeah.
Now, what about this here? Log base 3 of x equals -4. So then 3 to the -4th power equals x, changing it into an exponential equation. Oh, isn't that just 1 over 3 to the 4th, which is 1 over 81? Okay with that?
Yeah.
All right, now let's take a look at this one. Log base x of 9 equals 2. So if we change that into exponential form, what will we get?
The base of x raised to the 2nd power equals 9.
Okay, now we can solve this either going all the way back to chapter 6 and setting it equal to 0 and factoring it and take each factor and set it equal to 0, blah, blah, blah. Or we could solve it using chapter 10, I think it is, taking the square root of both sides, etc., etc. Let's do chapter 10. So you'd get x equals plus or minus 3, right?
Yes.
However, that's not correct. Why not? Well, we're going to go back to what we looked at, I believe, on Friday when we talked about y equals b to the x. We looked at basic exponential equations, and we said the base couldn't equal 1, and the base had to be greater than 0. Do you remember that?
Yes.
Okay, now let's go back here. So if we took, let's see here. How do I want to do this? Well, if I've got y equals b to the x, and I rewrite that in logarithmic form, that would be log base b of y equals x, right? I just took a basic logarithmic equation, or excuse me, exponential equation, rewrote it as a logarithmic equation. Base is the same. Okay, now, but we said that this can't be 1 and it has to be positive, right?
Yeah.
Yeah.
So this can't be 1 and it has to be positive. But where did this go? It's right there. So this can't be 1 and it has to be positive, which means this can't be negative. So the answer is just the positive 3.
Right.
So even though solving this equation, we get 2 solutions, we have to throw out the negative because we can't have a negative base on either an exponential or a log. All right, so be careful of that. Let's see here. Log base x of 100 of 1 over 100 rather equals -2. So changing this into exponential form, x to the -2 power equals 100. If I have a base to a power equals the same base to a power, the powers are equal. If I have a base to a power equals a different base to the same power, again, now the bases can be equal. So let's see here. 1 over 100 is 1 over 10 squared, correct? But 1 over 10 squared is 10 to the -2 power. So x to the -2 equals 10 to the -2, therefore x equals 10. That makes sense?
Yes.
All right, good. Because that's my story and I'm sticking to it. How about this one? Log base 4 of 8 equals x. So this would become 4 to the x power equals 8. Well, I would have a difficult time seeing how to take 8 and write it as 4 to some power. But what I could do is this. Let's break the 4 down and make it 2 squared to the x power. Okay, 4 is 2 squared. So 4 to the x is 2 squared to the x power. But now I would multiply the exponents. Okay, so 4 to the x is 2 to the 2x. But I could take 8 and write it as 2 cubed. So now if 2 to the 2x power equals 2 cubed, 2x equals 3, and x equals 3/2. So log base 4 of 8 equals 3/2, because 4 to the 3/2 power equals 8. All right with that?
Yes.
Okay. Now we're going to evaluate each logarithmic expression. Log base 3 of 9. Well, let's see. I'm going to make that equal to some unknown box. Okay. So if I take this and change it to an exponential expression, or rather equation, I get 3 to the box equals 9. You see how I got there?
Yeah.
But 9 is 3 squared, therefore the box equals 2. So log base 3 of 9 equals 2, because 3 squared equals 9. Log of 10, oh, not 10, it's log of 100,000. what is the log of 100,000? Well, you could punch this in on your calculator, but you could also say, well, that's equal to some unknown. What's missing, but what's there but isn't written? What's the base?
100,000.
No, the base. It's 10.
Oh, that's right, because it automatically. if it
Right, automatically. So that means 10 to the box equals 100,000. 100,000 is 10 to the 5th power, so the box is 5. So the log of 100,000 equals 5. Put that into your calculator, log of 100,000, and see if you do, in fact, get 5. You should.
Yes, I got 5.
Yeah, I got it.
All right, good. Let's see here. How about this? Log of, or log base 1/3 of 1/81. What does that equal? Well, it equals some unknown box. So that means 1/3 to the box power equals 1/81. But that's 1/3 to the 4th. Okay. Now, what's 1 squared?
1.
What's 1 cubed?
1.
What's 1 to the 4th power?
1.
So could I just put a 4 there without changing anything?
Yes.
But isn't that the same thing as 1/3 to the 4th power?
Yes.
Which means that. My box became a triangle there. Okay, because I've got the same base. So then the exponents are equal. All right. Let's see, we've already done some stuff where we took the log of something in our calculator. But let's take a look at this. Let's say we've got the log of x equals 2.8945. Okay, and we want to solve for x. So we can't punch this into our calculator yet, but couldn't we rewrite this as an exponential equation? What would the base be?
10.
So 10 to the 2.8945 power equals x. So now 10 raised to the 2.8945 power. And we're going to round this to 4 decimal places, 784.33211. So the 1 would round down, 784.3321 would be the answer. Now, there's 2 different ways I could put that in my calculator, and they're both about the same number of keystrokes. I could go 10, then the little caret, and then 2.8945 equals, or I could go second log, which then gives you the 10 to the x button, and it looks like that when you go second 10 to the, okay, and then you'd put in 2.8945, close it up, equals. So here you've got 2 keystrokes, let's see, actually you'd have to push the 1, then the 0, then the caret, so that's 3 keystrokes. This would be 2, and then adding this. So it's like, my point is, it's not a big deal which way you go. If you use the 10 to the x button, that's the second function key of log, or just the 10 with a little caret button. Okay, they both work. All right, let's see here. How about log of x equals negative 0.926? So then that becomes 10 to the negative 0.926 equals x, and to the near it to 4 decimal places. Let's see here. We've got negative 0.926, and I'm getting 0.11857. So the 7 would round up, 1186. Okay with that?
Yes.
Yeah.
All righty. Here is a story problem. It says children's height. The logarithmic function h of a equals 29 plus 48.8 times the log of the quantity a plus 1 gives the percent of the adult height of a male child a years old has attained. Okay, so what does all that mean? Well, it says, okay, it says, if a boy is 9 years old, what percent of his adult height will he have reached? So h of 9, if we put 9 in here and calculate it, we will get the percent of the adult height that this boy will have reached by age 9. Okay, so this is 29 plus 48.8 log of what, 10? So on the calculator, 10 plus 48.8 log of 10, and I get 58.8%. So that means that on average, a 9-year-old boy has reached 58.8% of his adult height. Does that mean that's true for every 9-year-old boy? No, but in general, on average, this apparently is true. You all right with that?
Yeah.
Okay. Let's see here. One more example here. Stocking lakes, as in putting fish into a lake, not as in a lake has a pair of stockings. That's an interesting picture. Okay, a farmer stocked a lake on her property with 75 sunfish. She was told that with a proper oversight, the sunfish population could be approximated by the logarithmic function f of t equals 75 plus 45 times the log of the quantity t plus 1, where t is the number of years since the lake was stocked. Find the number of sunfish she can expect in the lake in 2.5 years. So she wants to find f of 2.5, right? 2.5 years. So that's going to be 75 plus 45 times the log of 2.5 plus 1, which is 75 plus 45 times the log of 3.5. So we get 75 plus 45 times the log of 3.5. And I'm getting 99.48. So I suppose realistically, well, even without it, you rounding to the nearest fish, you get 99, right? I was going to say you can't have half of a fish. Well, you can, but it wouldn't be alive. All right. Anyway, that's all I've got for you today. I'll be back at 1:15 for my office hour. If you have any questions, otherwise, I'll see you tomorrow at 11:30.
Okay, have a nice day.
You too. Thanks so much.
Have a nice day.
You too.